Okay, so what we're going to have a look at this time is leading on from the last video where we looked at the chemical reactivity as we descended group 1, and we noticed that the chemical reactivity of lithium was less than the chemical reactivity of sodium, which was in turn less than the chemical reactivity of potassium, and we looked at the reactions of those three metals with water to prove our point. We saw that this was a very vigorous reaction, this a little bit less so the sodium, and then the lithium of course was the least of all. So our task today now really is a little bit more complicated in that we now have to explain and say, well, why was that the case? So let's look first of all at something that we did earlier in the year, which is why in chemistry it's so important to learn one topic, because it always leads into an understanding in the next topic. So what we'll look at is the electron, what actually happens when these things react in terms of their electrons. So if we look at lithium, lithium has a mass number, atomic number, okay, and if we'll just compare it with sodium, because the trend then for potassium is exactly the same, mass number and atomic number. Now what information does this tell us? Well, it tells us that lithium has 3 protons. Okay, it also tells us that it has 3 electrons, or in other words it has an electron arrangement of 2, 1. And then if we go to sodium, it tells us that it has 11 protons, and it also has of course 11 electrons, and those electrons are arranged in a configuration 2, 8, 1. Now the next thing we need to remind ourselves is what happens to these group 1 metals when they actually do react, when they were reacting with the water. Well, each of them loses 1 electron. So lithium loses an electron and goes to a lithium plus 1 metal. The sodium does exactly the same, loses an electron and goes to a plus 1 metal cation. Okay, so same thing happens. Now, we've already said that sodium is more reactive. We said earlier, if you remember, lithium, as we go down the periodic table, lithium to sodium potassium, that the chemical reactivity increases. So what that really means is that this electron is much more easily lost than the electron from the lithium, and then in turn the electron from the potassium must be even more easily lost than that. So our task today really is to decide, well, why is this electron more easily lost than the electron from the lithium, and then why is the electron from the potassium even more easily lost than the electron from the sodium? Well, let's have a look at first of all what is it that actually holds an electron into an atom. Well, this is why I covered the number of protons in each case. So let's have a look at the structure of an atom. Well, an atom is made up of a nucleus, which is made up of protons and neutrons. The protons are positive, neutrons are neutral. So the overall net charge on a nucleus is equal to the number of protons. So in the lithium, it's equal to 3 plus. And then it has an electron arrangement of 2, 1. So if we just pop those electrons on, as so. Okay, and then if we have a look at the same for the sodiums, right, where we have this time 11 positives, but then we have 1, 2, excuse my wobbly artwork at this stage, but okay, so we have an arrangement as so, and then we have 2, 8, I'll just draw our electrons in here, and the final electron is here. So what we're really saying, as we've already spoken about up here, is that it is this electron we're losing in the sodium, and it is this electron that we're losing in the lithium. So hopefully some of you are starting to see why it will be easier to lose the electron in the sodium than the electron in the lithium. And the reason is quite simply because of the distance from here to here. It's clearly further from the nucleus of the sodium to the outer electron than it is from the nucleus of the lithium to the outer electron. Now, some of you that are on the ball here will say, well, hold on a second, there are more protons in the nucleus of the sodium than there are in the nucleus of the lithium, therefore this electron in the sodium should be held more strongly. And that's a valid route of thought. However, it is the increased distance than the number of shells that is the dominant factor. So you've really got, exactly as hopefully some of you have picked up, two factors battling against each other, if you like. But the dominant factor is the increased number of shells, and therefore the increase in the distance from the electron to the nucleus, and that decreases what we call the electrostatic attraction of the nucleus, or the protons in the nucleus, to the outer electron. Okay, and if that's decreased, that means that it's much easier to remove the outer electron in sodium than it is to remove it in lithium, and same in turn, it is easier to remove the outer electron in potassium and rubidium and cesium, although they're not really on the syllabus. Okay, so hopefully that allows you to understand what was going on in video number 1, which covered the reactions of the group 1 metals with water and the observations associated with them. Now you can actually explain why those metals become more reactive as you go down the group.